Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Okay, step on the side, and we are going to review some trig stuff. Again, I've done some of this trig stuff before. It's something for my kiddos. You'll see it as an exam review. This is a non-calculator portion of this, so as we've had a lot of trig recently, we started with SOHCAHTOA, sine, cosine, tangent, but we did them also in non-right triangles and such. That was a lot more calculator-based, so you're not going to see that here. What you're going to see are the ones within the unit circle, and then the period function stuff, where we've been doing some graphs, and you'll get a word problem here as well. Completely without calculator for these ones here. There are, I can't remember how many problems, I'm going to say around 15 or so. They would go relatively fast at, where is it? They go relatively fast at some point, if you understand what's going on through it. I'd like to feel like as I'm doing this, I'm also doing the problems as well as a little bit of teaching here and there. All right, the first two questions, we're going to convert any degree measures into radians, like number 2, or radian measures into degrees, like number 1. So let's start with number 1, converting 61 pi over 36 into degrees. Now, the way I kind of refer to it with my students is, well, pi is 180. And I mean, you're like, hey, pi is 3.14. What do you mean? No, pi radians is 180 degrees. It's half of a circle. Pi radians is that distance there. So the conversion from radian measure, this length around a unit circle, to degrees, how many degrees is covered as a measure of the circle. 61/36 of a circle, of half a circle, I should say. So anyway, we're going to substitute 180 into here. 61 times 180 over 36. And you're wondering how to do this without a calculator. Well, it's really about the 180 over 36. I mean, you can imagine that this is presented to you because this cannot reduce, and you'd be right, this can't. But 180 over 36 surely can, and if you can't divide it outright, I mean, if you're unable to divide it outright, even though this is, divide it by 2, and then divide it by 2 again, and then until you get odd numbers, and then they're small enough that you know what you can divide by from there. I'll tell you right now that 180 divided by 36 is 5. That's something that I'm aware of. But let's say you didn't know that. Let's say you had to do the divided by 2 approach. Like, oh, I have to divide these, hopefully you can know that 180 divides by 6 or whatever, but you can divide it by 2, 90, and 18. At that point, I think you're ready to say that those can divide by 9 even, and then that's 10 and 2, and 10 divided by 2 is 5. At some point you get there. The point is you're avoiding doing the big multiplication here because you can do the smaller multiplication. And 61 times 5, 60 times 5 is 300. 1 times 5 is 5, so 305 degrees there. And just as making sense of your answer here, one thing to note, pi is 180 degrees, so 2 pi is 360 degrees. One thing that'll help on a lot of the problems that we do, especially when we hit, not these ones, but some coterminal bits here, is knowing how fractions work with things like 2 pi would also be 72 pi over 36, right? Because 72 is double that of 36. So 61 is less than 72. So 61 over 36 pi is going to be less than 360 degrees. And I accept this answer here. It's close to 360. It's not quite exactly like 61. It's not quite 72. I'm just kind of giving you a good heads up on how you can feel like your answer does make sense. All right, number 2, negative 285 degrees. I guess the answer is negative for what we're going to do. If you want a positive equivalent, I can eventually give it to you. But let's work this one out here. Now, this is converting into radians. We turn the 180, in essence, into pi. So the way to do that really is, a unit conversion takes that 180. We got to divide it out and multiply the pi within, basically. So, yeah, we're going to divide negative 285 by 180. So I have to reduce that fraction. Now, I'll tell you off the top of my head. I couldn't know for sure. I already thought of some numbers here, but I couldn't know for sure what the largest number is that could divide here. So I'll start small here, and I can divide them by, say, 5. I know these can both divide by 5, and we know, again, 180 over 5 should be 36 from what we just saw here. So, I mean, these numbers are a little bigger than what my students would probably prefer in, some of these scenarios here. I'm going to say when they test, they won't be quite this big when it comes to efficiency. I just want to make sure they know how to convert. By the way, this is going to be negative still. 285 over 6. See, 300 over 6 is 60. So they're 3 multiples of 5 that it's less than, so it should be 57. So negative 57 pi over 36. Anyway, keep working the magic here. If I said these can divide by 3, you know, we can work that out. Divide those by 3, and you get negative 19 pi over 12. And I think that's as far as it reduces. So I'm just going to go ahead and accept that one as the answer. So, you know, it's just, you got to reduce the fraction. I was going to try and divide them by 15 first. I don't know what the largest one was. Apparently must have been, what did I say? This was 3 and this was 5. Yeah, 15. 15 would have been the largest there. All right, so there are some conversions there. Now, when I do these ones right here, there are 6 of these kinds of problems. Find the value of each trig function. I like to look at them in terms of degrees when I eventually build my 30, 60, 90 degree triangles. We know that within these here, because it's calculator, non-calculator, I should say, there will be 30, 60, 90 reference angles potentially. Opposite the 30 is a 1, opposite the 60 is a root 3, and opposite the right angle is a 2 right there. So you're going to see this from me where you can go opposite or hypotenuse, or adjacent or hypotenuse, or opposite or adjacent, what have you. And the 45, 45, 90 would be some 1-to-1 to root 2 relationship as such. So we can work that division same way. You also possibly see any quadrantal angles, which means where you're... Actually, these won't have any. But you'll see, you've probably heard me talk about like a squished triangle, if you will, where the adjacent or opposite side may be 0. I don't think we're running into those there because we've done some with period functions, and I think we're just going to talk about them there. All right, sine of 300 degrees. Now, if you indulge me right now, what I'm going to do is I'm going to give you answers straight up. This is me doing these mentally, by the way, and then I'll explain how I went ahead and did these here. Whoops, not negative. I think it's just that. I want to make sure I'm correct. I sure hope I'm correct when all's said and done here. Oh, cosine. Shoot, I thought it said sine. I believe it's that. And then last one. I think it's negative 1. Okay, so here's what I'm doing with these here. And it's all a visual. It's either a drawn visual or a mental visual. For me, I made it the mental visual. Let's do the drawn version of it. Sine of 300 degrees. What we're going to do is rotate the terminal side 300 degrees over. This is 90, 180, 270. Now 300 is how far away from this x-axis here? Well, it's 60 degrees away because a full circle is 360. So here's a reference angle built down here in this portion of the triangle here. In a 30, 60, 90 triangle, opposite the 60 is a square root of 3. Opposite the 30 would have been a 1, and hypotenuse here is 2. Now, this square root of 3 is going vertically down here. That's a negative y value, so I'll make that one negative. Sine of 300 degrees is the same as sine of the 60 degrees inside here, basically. 60 is our reference angle, and relative to this, the opposite is negative root 3 right here. And the hypotenuse over hypotenuse is 2. We're referring to SOHCAHTOA right here. Sine is opposite over hypotenuse right there. So opposite the 60 is negative root 3. Hypotenuse is 2. So yes, it is negative. Another venture that I'll probably be pointing to several times. I say all students take calculus. This is a way of recalling that which trig functions are positive in which quadrants. All sine, cosine, and tangent are positive in the first quadrant. Only sine is positive in the second quadrant. Only tangent's positive in the third. Only cosine's positive in the fourth, which means sine is not positive in the fourth, and sine surely is not positive in the fourth here. Negative root 3 over 2. All right, the 1/2. Well, first of all, this is 5 pi over 3. So 5 pi over 3 is, well, actually it's the same as this. It's 5 pi over 3s. We know that pi is 180. So pi divided by 3 is 180 divided by 3. That's 60 degrees. 5/60s is occurring right there. That's how I'd like to think of a 5 pi over 3. There are a lot of other ways I can think about it there, but one of them is 5/60s, which is also 300 like that. So rotating around there, same exact triangle. There's actually no difference in that. That is the 1 to 2 to root 3 there, which is negative. The cosine is adjacent over hypotenuse, 1 over 2 like that, and that's where we're getting that 1/2. You know, at some point, these are ones that you kind of know. I kind of become aware, you know, pi over 3s, I kind of know what some, you know, I know what multiples of 60 are. it's 1 less than 6 pi over 3. 6 pi over 3 is 2 pi, which is 360, right? So 1 less than that. It depends on your number sense. And I tout to my students all the time. Some don't bother to care to listen to me what I'm talking about when I talk about number sense. Number sense is so important in math, especially when it comes to efficiency, making logical sense of some of your answers and things like that. And once you start to make number sense and, let mental math work you, and really, it's really beneficial. I'm talking to my kiddos here. By the way, I should just mention this here. I got to take a look in a second here, but this weekend I noticed that I hit 1,000 subscribers. Who knew? I never tag any single video. I never ask people to like, comment, subscribe. Hell, I never ask my students to like, comment, or subscribe. I sometimes say don't dislike. That's just rude, and that'll make me not want to record videos. But it's kind of interesting. It took about 10 years, but 1,000 subscribers. I apparently still can't monetize for whatever reason. I think I'd get cents on the dollar anyway. But just interesting. All right. Number 5, tangent of 4 pi over 3. So this is 4 pi over 3s. It's 4 60s. That's 240 degrees. Now, it's more than pi. 4/3 is more than 1, so this is more than pi. You know it's more than 180. I'm giving you little understandings of kind of trying to remember, what's happening in these instances. Anyway, this is 240. That's 60 down from 180 degrees, 60 underneath right there. You once again have 1 to 2 to root 3 relationship like this. However, not just the root 3 is negative this time, so is the 1. The 1 is also negative here. Now, I mentioned that my answer was the square root of 3. Well, tangent is that TOA, that is adjacent over hypotenuse. What did I just say? It is opposite over adjacent. Opposite the 60 is negative root 3. Adjacent to the 60 is the negative 1, and that gives you just a positive root 3. As we know, tangent should be positive in the third quadrant there. You are dividing two negatives. You might have noticed that I'm not ever making the hypotenuse negative. You never will. But Mr. Robinson, it's going down. Mr. Robinson, it's going left. Direction is in a different manner when it comes to hypotenuse. That is the actual terminal side right here based on this direction. It's a different way it's indicating direction compared to x having positive, negative, which are theoretical distances as they are ordered pairs on a graph. Different scenario entirely. This is a magnitude. This is positive. These are directions. I'm not going to explain myself there. Hypotenuse is positive, and if you don't believe me, look at the answers. Type it in your calculator and you'll see. All right, sine of 5 pi over 4. Now, a pi over 4 is a 45. So we're doing 5 45s, and maybe you don't know 5 times 45, but you certainly do know how to work around this little clock here. The 1 45, 2 45s, 3 45s, 4 45s, 5 45s, and it's 45 down. You don't even need to know how many degrees it is. It's just 45 down from 180 degrees. It's nice how they land on the quadrantal angles every so often until you get to that one right there. I should know that it's more than pi because 5/4 once again. So this is a 1 to 1 to root 2, like so. The ones are negative, as you kind of saw from before. Sine of 45 is 1 over root 2, like that. Or negative 1 over root 2 in this scenario here. So to give you that. Now you have to rationalize your denominator by multiplying top and bottom by the square root of 2. That makes the irrational number a rational number, and you get root 2 there. We're seeing the crux of the different kinds of values that you'll see. You'll see a 1/2, a root 3 over 2, a root 2 over 2. For tangent, sometimes you'll see a root 3 over 3. We haven't run into that at all. But a root 3 over 3, a 1, a negative, and all the negative versions. And then if we had quadrantal angles, you might see 1, -1, 0, or undefined, depending on what you have. So there are only, for special triangles here with no calculator, these are the only values that you're going to see. There's no other kind of value you're going to get. So eventually, when I'm talking about you have to rationalize this, it's really, you're going to condition yourself to kind of remember what this thing is. Like, it looks like that, right? It's, like that's the answer. You're not going to make up some other root 2 over 6. I've never heard of that before. That's not from a special angle. All right, let's see if I can properly get this negative root 3 over 2. Now, this says 29 pi over 6. That's big, right? That's bigger than doing just one full circle. We kind of mentioned before, well, it was with 36, but, you can represent 2 pi with a fraction over some other number other than 1, right? Over 6 here, 2 pi would be the same as 12 pi over 6. Why am I bringing this up? Because every 12 pi over 6 radians, because I want to keep in terms of 6 here, out of 6. I want to revolve around this circle multiple times so I can find out what 29 pi over 6 is coterminal with in a single revolution for a unit circle. So one whole revolution, 2 pi radians, would be the equivalent to 12 pi over 6. Another 2 pi, to make it 4 pi, is the equivalent to another 12 pi over 6, which is 24 pi over 6. So far I've traveled 24 pi over 6 radians. And you saw how fast I did this one at, here. This is something I do in my head there. How much left to get to 29 pi over 6? Just another 5 pi over 6. That's another 5 30s. 5 pi over 6. That's another 5 30s, which is 150 degrees. It's a little less than 180, as 5 6 is a little less than 1 here. It's 30 degrees up from 180 in the second quadrant right there. So that's a lot of, when I did 29 pi over 6, I said 12 pi over 6, 24 pi over 6, 5 pi over 6. Boom. And I know where 5 pi over 6 is. There's the goal. Here's my 1. Here's my negative root 3 as we go left. And here is my 2 right there. Cosine is adjacent over hypotenuse, negative root 3 over 2. The last one, tangent, and I'm fearing that I might have went backward. I don't think I did. I was fearing that I might have went the wrong way when I was supposed to go the backwards way, and I don't know. So tangent of negative 765, very same thing as what I talked about with the 2 pi thing. Every 360 degrees is another coterminal angle. Now, the only other thing about this problem is the negative. So instead of going counterclockwise right here, we shall go clockwise. And where we end up might be a different quadrant from, before. So going a full 360 degrees clockwise leads me to negative 360. Another negative 360 is negative 720. How far away are we from negative 765? We're only 45 away, and surely we were just going to be some sort of special triangle, special angle amounts away. So 45, in a 45, 45, 90 in the fourth quadrant, we have a 1-to-1 to root 2 relationship where this one here is negative. Tangent of negative 765 is opposite over adjacent, negative 1 over 1, which is negative 1. So all that explanation taken care of there, guys, is really, that's all of that. I did it in a nutshell there, those 6 problems. And you can see where you can get to with those explanations in full. All right, find the exact values of the 2 trig ratios not given. Simplify all radicals. That's really for number 9 where I'm asking you that. I'm going to ask you a different question here on number 10. Number 9, tangent of some angle is negative square root of 7. Not a special angle, not one that we've referred to. That means I am not, without a calculator, I couldn't tell you what this angle was. I could probably give you, it might be about this, and I'd be way off. But I can't tell you what the angle ever is. What we're going to do, we're not trying to find theta. We're trying to find sine of theta. We're trying to find cosine of theta. We're trying to find out that in the similar triangleness of the right triangle stuff, what is the opposite over hypotenuse ratio? What is the adjacent over hypotenuse ratio? That's what all these things always are. Granted, they're in a unit circle, but that's what these things always are right here. So tangent of theta is negative root 7. Now tangent being TOA is some sort of ratio opposite over adjacent. That means that negative root 7 doesn't have to just be written as that. It is negative the fraction root 7 over 1. Somewhere there is some right triangle, and I'll talk about the quadrants in a second, but somewhere there's some right triangle that can be built where if this is your angle theta, I can represent some root 7 here and some 1 here, and it doesn't have to be these exact values. The idea is that's the ratio, that this value is root 7 times larger than that one. Now you might ask, where's the negative? Well, the negative comes with regard to what quadrant I'm going to be in the unit circle. I don't yet know which one it is, but given that tangent is negative right here, now I'm going to look to it. Tangent is positive in the first and third quadrants. It's negative in the second and fourth quadrants. Which quadrant are we in among these two? You have to look at this other information right here that talks about the sine of theta being greater than 0. When you take the sine of theta and we get a positive result, sine is positive in the first quadrant, like all trig functions are, and in the second quadrant. The overlapping quadrant here that seems to be matching is quadrant 2. The quadrant that has sine of an angle positive and tangent of an angle negative is quadrant 2. That means that this angle is more built so right here. And notice I'm always drawing my altitudes to the x-axis there. So This is, the theta is technically the angle of rotation that we're referring to right there. Inside is our reference angle, but when we do tangent of whatever this angle, or sine and cosine of this angle within this reference angle, we got to keep in mind this will be a negative value. And that's what I have to hit. The opposite over adjacent is root 7 over 1. Which one's negative? The one apparently was negative. The one that you never saw. It wasn't there. But that's the ratio, and that's what makes this negative. Not the root 7. This is going upward, but this is going left. So we got to take sine and cosine of this angle right here, where we got to go opposite over hypotenuse and adjacent over hypotenuse. Well, gee, it sounds like we need the hypotenuse right here. I'm going to call this one x. So we got to use, say, Pythagorean Theorem to find out what this hypotenuse is. Never had to do with finding the angle. It was just about what is the sine and cosine of it, meanwhile. So I'm going to do Pythagorean Theorem, where you square root 7, you square negative 1, and then you get your x squared right there. Root 7 squared is 7. Negative 1 squared is 1, so we get that. X squared is 8. And I get to take the square root of both sides right there. So the square root of both sides will give me the square root of 8, not plus or minus. We're only referring to a positive value as its distance there. And x is going to be, that's square root of 4 times square root of 2, exactly written as 2 root 2 right there. So my hypotenuse is 2 root 2. That will help me when it comes to my sine and cosine of this guy. Let me move this guy over, speaking of which. I want to give myself just some more room to go because I'm not done with the problem. Okay, so 2 root 2, I should say. So when we do sine of this thing, we got to go opposite over hypotenuse. So sine of this angle is opposite over hypotenuse. Notice how it's all positive there, positive over positive. Now, I need to rationalize this denominator. I need to multiply, I don't need to multiply by the 2, just by root 2. I need to multiply top and bottom by root 2 over root 2 right here to clean up that bottom a little bit there. So this is going to give me root 7 times root 2 is root 14, all combined as one radical. Root 2 times root 2 is 2, but there's this other 2 right here as well. So this is 2 times 2, right, which is 4. So that's root 14 over 4. That's actually that answer right there. And yes, these are harder than what I would be testing my students with here, but that's not to say that these things can't be done. I mean, my students are on their way to go into pre-calculus. These are some expectations as far as being able to clean up values. Although it's not the highlight of the problem, right? The highlight of the problem started from the very beginning. This is just some more extra stuff to do. That's why the test won't necessarily reflect all that. It's trying to see how much you can do with the trig, not the radical stuff. Hey, what's cosine of our angle right here? Well, we have negative 1 over 2 root 2 like that. And same thing, denominator needs to be rationalized. I really just care about the root 2 part. See, if you do 2 root 2 over 2 root 2, it's not a big problem, but you will have to reduce a fraction thereafter, like, certainly. Negative 1 times root 2 is negative root 2. On bottom, it's that same thing. 2 times 2 right there, which is 4. So negative root 2 over 4 right there. And those should be our answers. Root 14 over 4, negative root 2 over 4. And no, these cannot reduce. Don't say, Mr. Robinson, how about root 7 over 2? How about we do a little bit of that? Doesn't work that way. Not with a ratchet. That is not a 14. That is the square root of 14. It's 3 point something. I don't know what it is. But root 7 is not half of root 14, like 2 is half of 4. Okay, number 10, and then we have some graph stuff on the back, I think, to talk about. Cosine of theta equals root 2 over 2. And our theta value is somewhere between 3 pi over 2 and 2 pi. What is the reference angle? What is the angle of rotation? Okay, this kind of question I might have asked my students on a calculator thing before to say, actually find out what your angle is with a calculator. And we're going to actually find out what this angle is here, but it's a special angle. It's a, this is in a special triangle, root 2 over 2. Where have we seen that? This is something that you're just going to have to kind of have knowledge of there, right? Even if I talk about building this thing and talk about adjacent over hypotenuse, root 2 over 2, you might say, well, I haven't seen that before. Where does that exist? You're right. I don't write them like that, right? It's the same as 1 over root 2. Where am I looking at? Same as 1 over root 2 right here. The root 2 over 2 is the ratio that occurs when you take the cosine of a 45-degree angle, of a pi over 4, if you will. And I want this thing to be in, well, I put this in radians here. I'm going to put this in degrees. I'll give you the radian equivalent, but I'm going to put this in degrees because that's how we build our triangles here. So it says, okay, we have a positive. Well, it doesn't matter whether it's positive or negative. They tell us what quadrant this is in. This is from 270 to 360 here. This is quadrant 4. This is right here in quadrant 4. Now, our root 2 over 2 is indeed positive for cosine in the 4th quadrant there. This is our angle of rotation right here, if I called that theta. That's the angle of rotation. Reference angle, I got to give it something. I'm going to give it an X right here. Reference angle is that guy right there. So the X is 45. The cosine of 45 is root 2 over 2, right? The 45 inside there, that's where we get the 1 over root 2. I'm speaking a lot, but I want to make sure that you're kind of making sense of how I'm processing that, right? That's where we get root 2 over 2. So the reference angle is 45 degrees, not negative. Not negative. All of our reference, you've never seen me put a negative even when I was down underneath. I'll say 60 down from 180. The reference angle isn't a physical triangle there. What is that actual angle measure? Even if I place negatives when it comes to distances for ratio's sake. It's positive 45. What is the angle rotation? Asks how far away you have to go from the original thing to kind of get this exact thing that we're talking about right here, right? The angle of rotation is what's 45 down from 360? Well, that's 315 degrees, right? 360 minus 45 is 315 degrees. So that's the angle of rotation, and that's the reference angle right there. And that's what we're referring to. Okay. All right, so that's all the trig. Well, it's not all the trig. That's all the stuff when it comes to the unit circle. Now we're going to get into the sketching of graphs. And, you know, I am going to I've made videos with these in great detail. I know I've done the other ones as well, but I really wanted to revisit those since I haven't seen them for a while. If you're following my video series, you just came off some of these. So I'm going to kind of mention these as if you've seen them before. Word problem I might slow down on a little bit, but the first two, let's rock and roll. Y equals negative 3 times sine of pi over 3x minus 1. Let's sketch this for all critical points across the graph Windows domain. Now, critical points to me include points on the midline and any peak and trough values for sine. And tangent, we can get a point above and below a point on the midline as well. I'll show you where. I'm going to start with this negative 1. This gives us a vertical shift downward to negative 1 right there, and that ends up representing our midline. We go up and down from this midline. We go on the midline as well as we go up and down, and we kind of process it from there. A sine graph has a good reference point on the midline itself because the sine of 0 is 0. Now, there is no horizontal shift in here, unlike that of this tangent graph right here, where we will shift pi over 4 units to the left when we get to it. But right here, we actually start, no horizontal shift, we will start actually on the midline itself. Now, the negative 3, the 3 represents the amplitude, how far up and down we will go at most. We'll go as low as negative 4 and as high as 2, because we go 3 up, 3 down. But the negative states that as a sine graph would generally start going positively, we'll start going negatively. But how far is based on this frequency right here of pi over 3. This is your b value, in essence, when we talk about the equation. This is your b value here. Now, what we want to do is use our frequency to determine the graph's period. The period for a sine or cosine graph by default is 2 pi. But if you divide it by the frequency, how many times that it occurs within a 2 pi range, pi over 3, you will get the actual period, how long it takes for the graph to complete a full cycle of its oscillation before it repeats again. 2 pi divided by pi over 3 is the same as 2 pi times 3 over pi, multiplied by its reciprocal. Pi over pi is 1, 2 times 3 is 6. So your period is 6, which means it takes 6 units to get back to midline and cover this, or it should be upside down, and cover this right here, and then it repeats that again and such. Now, I want to get some of the points in between. I want it to go down, trough out, come up, hit midline, come up again, hit the peak, and come back down and hit that midline. Now I want to get those exact points based on amplitude. So 6 is not an even, well, it's an even number. It doesn't evenly divide by 4, but it does enough. 6 divided by 4 is, 1.5. If you didn't know that, you could start by dividing it by 2. right? 6 over 2 is 3, which is the halfway mark as you go down and back up. 3 away from here is exactly in the middle where we hit midline again. And then 3 divided by 2 is, 1.5. No, 6 over 2 doesn't equal 3 over 2. Hopefully you saw my progression there. So 1.5 is the amount that I want to go before I hit every peak and trough. So 1.5 is right there. That's where we will go down first, 3 down from there, and we will hit that trough. And then we'll come up and go 3 up again, or 3 up the first time, and hit a peak and back down to midline, which would complete a single cycle of this right here. Going to the left, we can do the same thing and kind of work backwards. Where do we come from? We come from, looks like these points right here. Ooh, I almost went to there. So these are all the points within the window range that I can fit, or across the window's domain that I can fit. And we give ourselves a bit of that sine curve essence right there. That's a little angled for my tastes. That's a little too curvy for my tastes. I'm trying to do this without lifting the pen from the paper. Not my best effort. I'll take it though. All right, number 12. This is a tangent graph. Tangent has a much different look. It has that waterfall look that I refer to. I still do feature a midline though. It's at y equals 2. Everything's shifted upwards. You can see how the scale's different on this one. It's not by ones. This is what you'll see more of when it's not a word problem. A lot of pi situations. And I don't know if I stretched or changed this enough to a way that it's going to be nice to us. So let's see how it works out. So 2 is the midline there. Tangent of 0 is also 0, just like sine of 0. Cosine is the only one that's like off the graph when we do it. So would we start here though? Well, it's all about this left shift. We are going to go pi over 4 units to the left to start this guy right there. And tangent has a default period of pi. Unlike sine and cosine having a default period of 2 pi, it takes pi units before it repeats coterminal points and vertical asymptotes, which these things have. I'll draw those in a moment. So the frequency is 1. I don't see anything changing there, so the period here is still pi. What's pi units? When you look from 0 to pi itself, that's 4 increments here. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. So we're going to go 4 from each of these and hit another point on the midline. That's where that coterminality kind of takes place here. 1, 2, 3, 4, 1, 2, 3, 4. And we keep getting some of those as we can see fit. That one's sort of there. Right in between each of these midline points, exactly halfway down the middle, symmetry-wise, are vertical asymptotes. Now these are, I've mentioned these in the past here, the vertical asymptotes are lines that we don't cross, right? We approach. The midline is a little different story. It's not an asymptote. Even though you're allowed to cross horizontal asymptotes, this is not an asymptote on horizontally. So anyway, these are midlines that go immediately in between. Apparently every pi over 2 in between. But they are also pi units away from each other because that's where we start to hit that symmetry. Symmetry. The coterminality. That's where the period repeats again. This is every pi units. So what happens in between? Well, tangent has this nature of kind of crossing through and doing this stuff. And right in between here, tangent of pi over 4 is 1, and tangent of negative pi over 4 is negative 1, like that. But now we have an amplitude of 1/2, or a stretch factor of 1/2, which means instead of going 1 up, as we are, by the way, this isn't just 1 over, it's right in between the midline point and the asymptote. So we're going to go halfway up and halfway down. I want to get some characteristic of this that does show how the 1/2 actually takes place on here, and this will be exactly that. Now we approach the asymptote going upward through here. And then down, and yeah, and this thing continues over and over, like so. Okay, I have nothing to say for this thing right now, so I'm thinking about what to say there. Well, I do want to say that this is where we would have been referring to those. It probably goes more. Where we'd be referring to those quadrantal angles. Hey, what is tangent of 3 pi over 2? Do you guys know? Maybe you know what it looks like on the graph, and then you can refer to that graph to kind of state that answer in where you would otherwise maybe build one of those squish triangles that I like to do. Okay, there's that graph right there. Looks nice. Okay, last, well, I got one more problem before the last word problem here. Determine the features. Oh, I just saw a graphic on my screen for something. Determine the features of f of x equals negative 4 times the cosine of 1/3 x plus pi over 6 plus 7. I'm kind of doing the same order that you would probably look to graph. Amplitude and period are kind of one the same, but period I like to save for last because it's the most work. 7 is the midline. Specifically, it should be an equation, guys. It's y. It's not just 7. It's y equals 7, right? And starting point, that's an actual ordered pair. And, it's good to mention here. It's not just what is the h. It has to do with h. And actually, we got to do some work to come up with this. I'll show you why. But it's not just the h. It's where do you place it? Do you always place it on the midline? For sine and tangent, yeah. For cosine, And actually, cosine kind of uses, you kind of need this amplitude to refer to what cosine is. I almost want to graph this to explain it to you. But the starting point has to do with h. Now, the idea of our equation, the general one, at least for cosine when we look at it, it's a times the cosine of b times the quantity x minus h plus k. Well, the problem and the hurdle with this thing right here is that 1/3 is not factored out of our x minus h like this. It is very much a part of both terms here. So you have to factor that 1/3 out to reveal the true h that we're looking for. It's not pi over 6. But factoring a 1/3 out of this leaves you with x plus... it's not what is 1/3 of pi over 6. It's what happens when you divide 1/3 by pi over 6. Or 1/3 times what gives you pi over 6. You got to make this thing 3 times larger. What's 3 times larger? It's technically 3 pi over 6. But when you reduce that, it's pi over 2. You make the denominator 3 times smaller as you factor a 1/3 out of there. You know what? And that's algebra. I don't really know how deep to get into besides that. It's that is algebra, factoring out a fraction. It has nothing to do with pi. It has everything to do with how to factor a number like that out. Okay, so that's another version of that equation right there. Now that was important because I needed to determine what the actual h is, how much we shift to the left as we do it. And we actually go negative pi over 2 units over. Now the starting point also has this whole, are we on the midline itself? Is that a 7? Not for cosine. You see, for cosine, don't trust this graph yet. For cosine, we don't start here. We start either above at our peak or below at our trough, all depending on whether the a value is positive or negative. And we go a units up or down. This amplitude, I'm just going to say right here, is 4. Not negative 4, but it's 4. And the fact that we're going to start 4 below the midline here. We're going to start at 3. I tend to say it is 4 below when I count it. I don't even care that it's a 3, but the point is wherever you draw your midline, everything's now in reference to that. So that's literally the starting point of this thing. The period of this function right here has to do with the frequency 1/3. That is our b value. So if b, being 1/3, is 2 pi over p, then p is also 2 pi over b. Unless that's what we already did. I guess that's what we already did before, which is 2 pi times 3 over 1, which is 6 pi. The period of this graph is 6 pi. It is stretched 3 times larger than it would before. We're not going to graph it, but that's what that period would become there. So those are those 4 values. That's how you pick it apart. There was the factoring that was involved as well. A little tricky there. All right, last problem here. No calculator ever used. Naturalists find that populations of some kinds of predatory animals vary periodically with time. Assume that the population of foxes in a certain forest varies sinusoidally with time. Records started being kept in the year 2002. Let this be t equals 0. So this year is 2002 right here. So 5 is 2007, 30 is 2032, etc. Okay, I know I'm covering part of that. Sorry. A minimum number of 200 foxes appeared in 2004. The next maximum, 800 foxes, occurred in 2010. Sketch a graph of the function f of x for the fox population since 2002. F of x, fox. I love it. Okay, so 2004 is how many years since 2002? Well, it's 2 years since then. In year 2, we had 200 foxes. Now you can see that this is scaled. This is your f of x, by the way, and this is x, which is kind of your years. But, well, it is. Years since 2002. These are scaled by 100s, 100, 200, 300, 400, 500. So 200 foxes appeared in 2004, which is 2 years away right there. That is a point that's on this graph. 800 fox... Now I just swore. 800 fox. 800 foxes. Great. Now I'm demonetized. 800 foxes occurred in 2010, which is 8 years from 2002, which is up here. So 800, I believe, is also right there. All right, dude, sketch the graph. Here we go. No, it's a sinusoidal graph. That means that, you know, this is the minimum, this is the maximum, this is a trough, this is a peak. And I said the next maximum, so you know it's not in between, it's doing a bunch and just hits right there. We know it's the very next one, which means that this is half of a full period. When it comes to our sine functions, cosine functions, sinusoidal, you know, it's got to hit from peak to trough, trough to peak, back to trough again, and that would complete a full period, a full cycle there. And then it would do it again and again. I'm going to get these points in full, though, so this is half of it. Half of it took how many years? From 2004 to 2010? That's 6 years. 1, 2, 3, 4, 5, 6. Another 6 years, 1, 2, 3, 4, 5, 6, should be the next minimum by the model. And the next peak should be another 6 years later there. 1, 2, 3, 4, 5, 6. And a trough, 1, 2, 3, 4, 5, 6. Right there. And a peak. I don't think we can really fit another peak right there. But those are some points there. Now, the midline should be midway between your peak and trough for these graphs as well, right? So this one here should be right at 500 foxes. That's the midline here. And the midline should have values, too, that are immediately right in between. If these are 6 years apart, then 3 years apart, we should be hitting midline values. We should hit 500 foxes every 6 years. But 3 years from a peak or from a trough right there. I don't know why the fox population changes so much, but we can get those as well. This really helps us to draw that graph, and this is as much as I can really fit. I could technically plot that point right here before 2002, just to get the idea of the curve. I'm not going to count this one. I'm actually going to erase this part. I just want to give myself an idea of how I want to draw this first of all. And then I'm going to go and complete it. So we draw the graph based on the information. I don't create an equation based off the information first. Honestly, I don't know if I could do that myself. I bet I could, but it really helps to see the graph, especially when it comes to midline for amplitude and things like that. I mean, I could do it without, but that's okay. The graph really helps if someone's asking me, how do you do this? Step 1, get that. So year 0 would probably be somewhere close to 300 foxes, probably a little bit more than that, but it's not something we actually know there. It started, did it start? Records started being kept in the year 2002, so like boom, right there, even though I don't know the actual point. All right, and it continues forward so we can predict things in the future. By the way, this is the year 2002. We're in 2022, which is 20 years later. Guess what? We're maximizing our foxes, baby, especially, but there's one fox above all that y'all got to look up. And please subscribe to Save a Fox. His name is Finnegan Fox. And I do Finnegan Fox Fridays with my students every Friday, where I play a video of the adorable one and only Finnegan Fox. All right, that's sketching a graph there for the fox population since 2002. Let's write a sine and cosine equation for f of x just to get the practice in. So as far as these, I say write a sine and cosine equation, not the, because I can write a sine equation based off this point, or this point, or this point, or this point, or this point. Any points that exist on the midline, because sine of 0 is 0, sine starts on midline. I can make a cosine equation from this point, this point, this point, this point, or this point. I'm going to do the ones that are closest to the year 2002. It's less shift, and yeah, this is just less shifts overall. So when it comes to a sine graph here, I'm going to go ahead and do that in this darker blue. I'm going to be referring to this point here, which by the way, the sine and cosine graphs both together kind of share a lot of the same information. They share the same amplitude, they share the same frequency, and they share the same midline. What changes is one says sine, one says cosine. The amplitude may show the A may be negative or positive based on where you're starting, and the H value, how much you shift over, is the only thing that really changes. So in both of these right here, universally, the amplitude between midline and peak or midline and trough is 300 foxes. Now, is it negative or positive is based on where we start here, because our starting point for sine is going to have us go up. This will be a positive 300 overall, but the A is 300. The absolute value of A, let me say that. I'll save the B for a moment. I'll get to H and K because they're very fast. The H is actually based off whether we're doing sine or cosine. So H, or based on your reference point, I should say. The H value here is 5. 5 years into it, we're going to take. The K value, the midline, is 500. And B, the frequency is 2 pi over your period. Now, the period isn't just from a min to max, it's completing a full cycle, such as this one right there. That's a full period. Or this is a full period. Or this is a full period. Whatever it takes to repeat. How long does it take to go from year 2 to year 14? That's 12 years. So we are going to be dividing 2 pi over p, 2 pi over 12, which is pi over 6. Pi over 6 is the frequency, not the period, but that is the part that goes into your equation. So the sine equation should look like f of x equals 300, it is a positive 300, times the sine of pi over 6 times the quantity x minus 5 plus 500. All right. Cosine. Cosine equation, I'm going to pick this one. It is a trough. You could pick a peak right here. This may be, well, this wouldn't give you a negative cosine. This one will, because we start underneath right there. Now, is it 3 below? No, it's 300 below. Anyway, so cosine is the same information here, except now here h is 2. H is 2. And remember, these are years. It's not 2004. 2004 is 2 years from 2000. So this will be f of x equals negative 300 as we start below on cosine instead of above. It's not about going up. It's about kind of its placement. Times the cosine of, same stuff, pi over 6 times the quantity x minus 2 plus 500. Both equations are the same exact graph. Right? All right, use either equation to predict the fox population in 2024, so 2 years from now. So I'm going to do the sine one just because the positive that's right there. So 2024, you have to think of that's not what x equals, right? It's how many years since 2002? That's 22 years since then. So we're going to substitute 22 in for x into this. We'll get f of 22. I'm going to use the sine equation equals 300 times the sine of pi over 6 times 22 minus 5. I'll just go ahead and tell you that's 17. Plus 500. Heck. That's 17 pi over 6. Let me change that right in there. 17 pi over 6. Now, this is still the non-calculator portion, right? We've done everything without a calculator so far. We can take the sine of 17 pi over 6. Heck, we took the cosine of 29 pi over 6. I think that was it. 17 pi over 6. I really want the parentheses there. So what's sine of 17 pi over 6? Well, 12 pi, well, this is a 5 pi over 6 thing again. 12 pi over 6 is a full circle, full 360. Plus another 5 pi over 6 gets you there. So this is, if you can visualize it, 5 pi over 6, 5/30 is 150 degrees. That's 30 up from 180, which is a 1 to 2 to root 3 relationship, the root 3 being negative. Doesn't matter because we're doing sine. Sine of this is 1 over 2. It is 1/2. 1/2. So this is 300 times 1/2 plus 500, which is half of 300 is 150 plus 500, which is, let me scroll down, which is 650 inches, years, foxes. 650 foxes predicted in 2024. Last question, and then I'm done. In which years since 2002 till present day, so from 2002 to 2022, has the population been modeled at 350 foxes? So here, now f of x is 350. You are now substituting that in to your equation. Dare we use sine again, or do we go to this, or dare we try cosine? Let's give cosine a shot. Why not? 350 equals negative 300 times the cosine of pi over 6 times x minus 2 plus 500. Your goal is to get x by itself. You gotta attack everything outside of there to get x by itself. It's not much. You gotta work it. Subtract 500 from both sides and you get negative 150. It's actually probably good that I chose the cosine one because I'm going to divide a negative by a negative here in just a moment. Okay, now it's negative 300 times this, right? Divide both sides by negative 300. And negative 150 divided by negative 300 is positive 1/2. So I get a 1/2 there, whoop, whoop, equals cosine of pi over 6 times the quantity x minus 2. To get cosine away on this side here, you got to take we're going to take the inverse cosine of both sides. Inverse cosine of this side, inverse cosine of that side. Now I'm going to cancel out the cosines there. I am left with pi over 6 times x minus 2. And here we're taking the inverse cosine of 1/2. Once again, something you got to be able to do. The cosine of what angle, what basic from 0 to 90, whatever, what basic reference angle gives you adjacent over hypotenuse? 1/2. In what case do we have that? Well, this would be the √3. That's a 60-degree reference angle. We're in radians, though, as you can tell. So 60 degrees is pi over 3. So we get pi over 3 right there when we're talking about this guy here. You can tell I moved this over here and moved that over there. I got to keep getting x by itself. So I'm going to multiply both sides by 6 over pi. 6 over pi. And here, boop, 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 you're left with x minus 2 equals 6 over 3, which is 2. Add 2 to both sides, you get x equals 4. Now, what does that mean? Well, I'll show you on the graph what it means. And notice that I said which time since 2002 till present day, because there's more than one answer. You have to remember, inverse cosine is only going to give you one number, despite the fact that it's not just cosine of 60 that gives you 1/2. It's also cosine of 300. It's also cosine of 420, and cosine of 660, and cosine of 780, and cosine of 1020. All those ones that are in the first and fourth quadrant with a 60-degree reference angle rotating over and over and over again. And that's what this cycle means, going back and forth. This is the next 360 over and 360 over when it comes to taking cosine of those values right there. All of those things are coterminal. It's 4 isn't the only place. X equals 4 is not the only place when it happens. And x equals 4 isn't even an answer for us. We need the actual years. In which years since 2002? I guess you could say 4 years since 2002, but what are the actual years? Well, one of the years, 2002 plus 4, is 2006. And I'm going to show you on the graph. In the year 2006, there were 350 foxes. Now, my graph isn't perfect, but 4 years since then, does it make sense that that is maybe 350? Oh, yeah, totally. Is that the only place that we hit 350, just right there? No. What about over here? Now, I don't know what, I will tell you what the exact year is in a second, and over here, and over here. As you can tell, my graphs might not be perfect here, but these are other points. Now, since 2002 till our year, which is 20 years later, means I'm not going to count these ones. These are only predictions. These are the only ones that are attacking the model. So I'm not going to estimate these. I can figure out what they are. Here's the idea. The 4 is 4 years since... Well, 2002. Let's see. That actually might make it a little tough to talk about. Oh, okay. Well, it's this. It's 2 years since a trough. It's 2 years since a trough, right? A trough on this side. That must mean this is 350 right here. Also, this should have hit more 350, not 300. 2 years since a trough. So another trough. If I go 2 years away from the trough right here, and 2 years away from the trough right here, then those are hitting. Mine aren't, but it should be hitting at 350 right there and right there. So that is year 12. Not year 12 like AD, but 12 years since 2002 and 16 years since 2002. So those are the other 2 points that we're going to hit. So 2002 plus 12 is 2014. 2002 plus 16 is 2018. So 2016 and 2018. Difficult problems indeed, as far as in comparison to what my students would be tested with there. Now, I'll tell you what, they get a 55-minute class to do a test. I conquered this in 53 minutes and 55 seconds. And that was with teaching it right there. So, okay. So anyway, that ought to do it for this one, guys. This is Mr. Robinson. Thank you so much for watching. I sure hope that this made a whole lot of sense to you, and a calculator portion should be coming up within a day or two of this upload. So I hope that you look forward to that one, where we revisit some law of sines and cosine stuff, maybe a couple things in unit circles when we saw things with like the reference angle business, right? All that again. All right, that's it from me. Thank you so much. Take care.